Hello there, and welcome back to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can loosen their grip and curiosity can drift gently into rest. Tonight, we're going to explore a question that sounds simple at first, but opens into something vast and strangely comforting. Does the past truly disappear, or is it still travelling with us, woven into light, matter, and the deep fabric of space itself? Before we begin, if these slow explorations bring you a little peace at the end of the day, you're always welcome to like the video and subscribe. And if you feel like sharing, let me know where in the world you're listening from and what time it is there right now. It's always a quiet wonder to see how many different nows gather here at once, each in its own corner of the earth. Now, dim the lights if you can. Let the room grow softer. Maybe there's a faint hum in the background. A fan, distant traffic, the sound of your own breathing. Let it all settle into the edges of your awareness. There's nothing to solve tonight, nothing to rush toward. We're only going to walk slowly through an idea, turning it over in our hands like a smooth stone. We tend to think of the past as something left behind, a set of moments that slipped through our fingers. Yesterday feels sealed. Last year feels unreachable. A childhood memory feels like a photograph in a drawer. The word past itself sounds distant, like something that has already faded into shadow. But physics has a way of gently unsettling that intuition, because when you look up at the night sky, you're not seeing what is happening now, you're seeing what happened. The stars overhead are not presenting their present lives to you. They are sending you light that began its journey years ago, centuries ago, sometimes millions or billions of years ago. The sky is not a live broadcast, it is an archive, and that raises a strange possibility. If so much of what we see is already old and yet still arriving, still moving, still crossing space, then perhaps the past is not as gone as it feels. Tonight, we'll follow that thread. Through light, through gravity, through atoms and entropy, and the quiet mathematics of information. And we'll do it gently, translating the hard edges of physics into images and comparisons. You can simply rest inside. You don't need to hold on to every detail. Let the ideas wash over you. The universe is not in a hurry. We don't need to be either. In everyday life, we move through the world as if the present were solid and immediate. You reach for a glass of water, you hear a voice across the room, you glance at your reflection in a mirror. It all feels instantaneous, immediate, now. But even here, in the quietest, ordinary moment, the present is already slightly delayed. Light, the fastest thing we know, does not move infinitely fast. In empty space, it travels at about 300,000 kilometers per second. That number sounds enormous, and it is. Light could circle the Earth more than 7 times in a single second. But even at that speed, it still takes time to cross distance. When sunlight warms your face, that light did not leave the sun in that same instant. It began its journey a little over 8 minutes ago. The warmth you feel now is sunlight. From 8 minutes in the past, if the sun were to vanish, which it will not, so there's no need to worry, we would not know for 8 full minutes. The present sun we see is already slightly old. Even across a small room there is delay. When a friend speaks, the sound waves need a fraction of a second to reach your ears. The light reflecting off their face needs another tiny fraction of a second to reach your eyes. Your brain then takes a little longer to process what it has received. By the time you experience the moment, it has already slipped into the past by a whisper of time. The mirror in front of you is also a time machine, though a very small one. The light leaves your face, travels to the glass, reflects, and returns to your eyes. The image you see is not perfectly now. It is you, a few billionths of a second ago. These delays are so small that they do not disturb our daily life. They're too gentle to notice, but they are always there, quietly reminding us that the present is not a razor-thin line dividing past from future. It is more like a soft blur. If we widen the distance, that blur grows larger. The nearest star beyond the Sun, a star called Proxima Centauri, is a little over 4 light-years away. That means the light reaching us tonight left that star more than 4 years ago. When you look at it, you are seeing it as it was 4 years in the past. It may have changed since then. It may have flared or dimmed. But the information about that change is still travelling. And if you point a telescope at a distant galaxy billions of light years away, you are looking so far into space that you're also looking billions of years into time. You might see a galaxy in its youthful stage full of bright blue stars, even though in our present moment it has already aged into something quieter. The light simply has not finished its journey. This is one of the quiet miracles of physics. Distance and time are braided together. The farther away something is, the further back in time you see it. Looking deeper into space is not just exploring faraway places. It is reading older chapters. There is no formula you need to remember here, no symbol to hold in your mind. Just this gentle idea. Light takes time to travel. And because of that, every act of seeing is an act of looking into the past. The sky, then, is not a ceiling. It is a library. Every photon, every tiny particle of light, carries with it a record of where it came from and when it began its journey. It does not forget. It does not stop midway and reconsider. It continues forward, crossing space, until something or someone intercepts it. And in that sense, the past does not sit quietly behind us. It radiates outward, it moves, it travels. Even right now, light reflecting off your face is leaving Earth and heading into space. Most of it will wander forever, never striking anything. But somewhere, unimaginably far away, a small fraction of those photons may one day brush against another world. And if there were an observer there with a powerful enough instrument, they would see a faint image of you as you were in this moment. The thought is not meant to be unsettling. It is meant to be expansive. The present is slightly late. The past is still in motion, and the universe is full of messages that have not yet arrived. If the present is always arriving a little late, then light is the quiet reason why. It is the courier that carries every visible story across space, never rushing, never pausing, simply travelling at its steady and unchanging pace. In the emptiness between the stars, light moves at what physics calls a constant speed. No matter how bright the source, no matter how far it travels, that speed does not increase or decrease. Scientists measure it at roughly 300,000 kilometers per second, a number so large it feels abstract. But what matters more than the number is the steadiness. Light does not sprint or stroll. It moves with a kind of cosmic discipline. Because of that constancy, distance becomes a clock. When astronomers say something is 1 light-year away, they do not mean a unit of time. They mean the distance light travels in 1 year. It is a gentle merging of space and time into a single idea. A galaxy 10 million light-years away is not only 10 million light-years distant in space, it is also 10 million years distant in history. Imagine shelves in an immense archive. On the nearest shelf sit the moon and the sun. They're light only seconds or minutes old. On the next shelves sit nearby stars, their stories delayed by years. Further still are distant clusters of galaxies, their light carrying news from before our species existed. And on the farthest shelves lie the faintest galaxies of all, whose light began travelling long before Earth had oceans. Telescopes do not look outward so much as backward. When an astronomer studies a galaxy billions of light years away, They are not seeing it as it is today. They are seeing it as it was billions of years ago. The image might show spirals forming, stars blazing with youthful brightness, clouds of gas swirling in slow arcs. But that image is already ancient. In our present moment, that same galaxy could look completely different. Its brightest stars may have burned out, new stars may have been born, entire regions may have collided and reshaped. The light simply has not finished the journey that would inform us. There is something strangely comforting in that. It means that the universe is not silent. It is always speaking, but it speaks in delayed whispers. Even here on Earth, this principle quietly shapes our understanding. When engineers measure the distance to the moon using lasers, they send pulses of light toward reflectors left on the lunar surface by astronauts decades ago. The light travels to the moon and back. By measuring how long that round trip takes, they calculate the distance. No complex equation needs to echo in your mind. Just this. Light travels steadily, and the time it takes to arrive tells us how far it has been. Light is more than illumination, it is memory in motion. Every photon carries information about its source, its colour, its intensity, its subtle variations. From those tiny details, astronomers can learn astonishing things. They can determine how fast a star is moving by noticing how its light shifts slightly toward red or blue. They can identify which elements exist inside distant galaxies by observing the fingerprints left in their spectra, patterns unique to hydrogen, helium, oxygen, and other elements forged in stellar furnaces. It is as if each beam of light is not only a messenger, but a letter describing both the sender and the journey. Sometimes that journey is straight and simple. Other times it is curved. Massive objects like galaxies and clusters can bend light through gravity, a phenomenon known as gravitational lensing. When this happens, light from a distant galaxy arcs around a massive object in between, reaching us along multiple paths. We may see the same galaxy in 2 or 3 slightly different positions in the sky, like a reflection in warped glass. In rare cases, those multiple paths have different lengths. That means the light travelling along one route arrives slightly later than light along another. The same cosmic event can appear to replay itself. A distant star may brighten in one arc of the lens, and then brighten again in another arc weeks or months later. It is not that the event happened twice, it is that light took 2 different roads. The universe, in this way, offers its own quiet reruns. And the farther we look, the older the messages become. Some of the faintest galaxies ever observed are seen as they were when the universe was only a few 100 million years old, still in its early chapters, forming its first generations of stars. Their light has travelled for more than 13 billion years to reach us. It began its journey long before Earth formed, long before our sun ignited, long before there was anyone to wonder about it. That light was already on its way when our planet was still only a possibility hidden in a cloud of gas. It is humbling to realise that when you step outside at night, you're standing beneath a sky filled with arrivals, photons that left their sources before mountains rose, before forests spread, before language formed. They are arriving now. Your eyes are the final stop in journeys that began across unimaginable distances. And just as light from distant stars reaches us, light from Earth does not stay here. Every second, our planet reflects sunlight back into space. Photons bounce off oceans, deserts, cities, forests, and faces. Most of them will drift forever into the dark, but they carry images. Somewhere, far beyond our current reach, Earth's past is spreading outward like an expanding shell of faint pictures. The world you inhabit is continuously broadcasting itself. The present, then, is not confined to a point. It is a sphere, expanding at the speed of light. Each moment radiates outward in all directions. What we call the past is not locked behind us. It is travelling through space, layer upon layer, each second forming a new expanding wave of information. Light is patient. It does not forget where it came from. It simply keeps going. And if light is the universe's most faithful messenger, then perhaps the past is less like a vanished shadow and more like a letter still in transit. The sky above you is not silent. It is full of arrivals. And somewhere, even now, your own moment has already begun its journey into the deep. There is something familiar about an echo. If you have ever stood in a canyon or inside a large empty hall and spoken aloud, you may have heard your own voice return to you a moment later. The sound leaves your mouth, travels outward, strikes a distant surface, and then comes back, softer, delayed, slightly altered. The echo's not a new sound. It is the old one, arriving by a longer path. Light can behave in a similar way. We often imagine light moving in straight lines, like a taut string stretched from one point to another, and most of the time it does. A photon leaves a star and travels outward until it encounters something that absorbs it or reflects it. But space is not perfectly empty. Between the stars drift vast clouds of dust and gas, made of particles so small they would look like smoke if you could hold them in your hand. When a brilliant event happens, in space, for example when a massive star reaches the end of its life and explodes in a supernova, an enormous burst of light radiates outward in all directions. Some of that light travels straight toward us. We see the explosion, perhaps as a new point of brightness in the sky. But not all of the light takes the shortest road. Some of it strikes distant clouds of dust, scattered light years away from the original star. A tiny portion of that light bounces off those particles and begins travelling toward Earth along a new route. That route is longer, it curves through space, and because it is longer, it takes more time to arrive. Years later, sometimes even centuries later, astronomers may observe a faint glow appearing near the original location of the supernova. At first glance, it might look like the star has exploded again, but it has not. What we are seeing is the original light, returning by a different path. This phenomenon is called a light echo. It is not metaphorical. It is literal. The universe replaying a moment. The physics behind it is gentle and straightforward. Light moves at its steady speed, about 300,000 kilometers per second, whether it travels directly or along a winding detour. If one path is longer than another by even a few light years, that difference translates into years of delay. The event happened only once, but the information about it arrives more than once. In some cases, light echoes have allowed astronomers to study explosions long after they seem to fade. There are historical supernovae recorded by ancient observers, bright stars that suddenly appeared in the sky and then vanished. Centuries later, modern telescopes have detected faint reflections of those same explosions in surrounding dust clouds. By analysing the echoed light, scientists can reconstruct details about the original event. How bright it was, what elements were present, how violently it expanded. It is as if the universe kept a copy, and the copy is not abstract. It is the same photons, or at least photons carrying the same pattern of information, scattered and delayed. Imagine a brilliant flash in a dark room filled with thin mist. Some light travels straight to your eyes, some strikes the mist and scatters. A moment later, you see a faint shimmer in the air, a ghostly replay of the original burst. That shimmer is not imagination. It is the past arriving by another road. On larger scales, the effect becomes even more dramatic. There are cases where light from distant quasars, intensely bright centres of galaxies powered by enormous black holes, has been bent and delayed by massive galaxy clusters between us and them. Because gravity curves space, it also curves the paths of light travelling through that space. Light can loop around a massive object and take multiple routes toward Earth. If those routes differ in length, the quasar may appear to brighten and fade multiple times in slightly different images. Again, it is not that the quasar is flickering in the present, it is that we are receiving its past in layers. This idea subtly changes how we think about disappearance. When something fades from view, we tend to assume it is gone. But in a universe where light continues outward indefinitely unless absorbed, fading does not mean vanishing. It often means distance. The event is still travelling, just farther away. Every bright moment radiates in expanding shells. Picture a sphere growing outward at the speed of light. The surface of that sphere marks the boundary between not yet arrived and already past. Inside that sphere lies the region of space that has received the event. Outside it lies the region that has not yet heard the news. Each second creates a new sphere. In this sense, the past is not a fixed location behind us. It is a set of expanding waves. Some of those waves intersect with dust clouds and return as echoes. Some curve around, massive structures, and arrive in duplicate. Most simply continue onward, thinning and cooling as space expands. And this process is not limited to rare cosmic explosions. It is happening constantly, quietly, everywhere. The light reflecting off your window tonight is leaving Earth and travelling into space. Some of it may scatter off interplanetary dust. Some may curve slightly under the influence of gravity. Most will move on, undisturbed. But in principle, if there were clouds of dust arranged just so, even your small everyday moment could echo faintly back towards some other corner of the cosmos. The universe is not a single stream of events flowing neatly from past to future. It is more like a vast hall filled with reflections and delayed arrivals. There is something deeply tender about that. It suggests that no moment is entirely singular. Every event radiates consequences and information outward. Some of those consequences we can measure, others fade beyond detection, but none of them simply fall into nothing. Light does not forget the path it has taken. It only follows the geometry available to it, and in those bends and reflections we glimpse a quiet truth. The past does not only move away from us, sometimes it circles back. The sky, then, is not only an archive, it is also an echo chamber, not in the noisy sense of repetition, but in the gentle sense of memory finding new paths. When you step outside at night, the faint glimmers overhead may not all be first arrivals. Some may be second whispers, softened by distance and dust. They are reminders that time does not always travel in a straight line toward disappearance. Sometimes it lingers, sometimes it returns, and sometimes it arrives long after we thought the story had ended. Light is not the only thing that travels outward from an event. For a long time, it was the only messenger we knew how to read. Every star, every galaxy, every nebula revealed itself through light. But in the early 20th century, a new idea quietly emerged from the mathematics of gravity. An idea that suggested space itself was not rigid and unmoving, but flexible. According to Einstein's theory of general relativity, gravity is not simply a force pulling objects together. It is the bending of space and time caused by mass and energy. A planet does not orbit a star because an invisible rope ties them together. It orbits because the star curves the surrounding fabric of space-time, and the planet moves along that curve. If you imagine placing a heavy ball on a stretched sheet, the sheet dips. A smaller ball placed nearby rolls inward, not because it is pulled directly by the heavy ball, but because the sheet itself slopes toward it. That image is not perfect, but it captures the essence. Mass shapes space. Now imagine something far more dramatic. Two enormous black holes, each many times heavier than our sun, spiraling around one another in deep space. As they circle closer and closer, they distort space-time more and more intensely, and when they finally collide, the disturbance does not remain localized, it ripples outward. Those ripples are called gravitational waves. They are not waves moving through space the way sound moves through air. They are waves of space itself stretching and compressing as they pass. If one were to travel through you, the distance between your head and your feet would change by an unimaginably small amount, and then return to normal. You would never feel it. The effect is far too tiny. But the wave would still carry information. In 2015, after decades of preparation, scientists using an instrument called the Laser Interferometer Gravitational Wave Observatory, often shortened to LIGO, detected such a ripple for the first time. It appeared as a faint signal in the data, lasting only a fraction of a second. Yet encoded in that tiny vibration was the story of two black holes merging more than 1 billion light-years away. The event itself had happened over 1 billion years ago. The gravitational wave had been travelling ever since. To understand how delicate that detection was, consider this. The stretching and squeezing measured by LIGO was smaller than the width of a proton compared to the length of its 4-kilometre-long arms. If those arms were stretched at the distance between Earth and the Sun, the change would be less than the width of a human hair, and yet the instrument could sense it. The ripple was not just a signal about the past. In a profound sense, it was the past still moving. Light can be absorbed, scattered, bent, or blocked. Gravitational waves are far less easily disturbed. They pass through stars, through dust, even through entire galaxies with almost no alteration. They do not carry an image in the way light does. They carry a rhythm. When two black holes spiral inward, they produce a rising chirp, a pattern that increases in frequency and intensity as the holes approach each other and finally merge. That pattern remains intact as it travels across space. When we detect it, we're not reconstructing the event from fragments. We're feeling the original rhythm, preserved. In that sense, a gravitational wave is not merely a message about an event. It is the event's motion, still unfolding across the universe. Picture dropping a stone into a calm lake. The splash happens in an instant, but the ripples spread outward long after the stone has sunk. If you were standing far away at the edge of the lake, you would see the wave reach you much later. The splash is over, the ripple is not. The universe is filled with such ripples. Since that first detection, dozens of gravitational wave events have been recorded. Black holes merging, neutron stars colliding. In one remarkable case, two neutron stars spiraled together and produced both gravitational waves and a flash of light. For the first time, astronomers could hear and see the same cosmic event. The light told one part of the story, the wave told another. It is humbling to realize that these waves pass through us constantly. Most are too faint to detect with our current instruments, but they are there, subtle expansions and contractions of space itself, washing over Earth and continuing outward. Unlike light echoes, which depend on dust and reflection, gravitational waves are almost never turned back. They simply continue. The ripple grows larger in radius, thinner in intensity, but it never stops. This means that somewhere, billions of light years away, the echo of that ancient black hole merger is still expanding. It will continue expanding long after our sun has dimmed, long after our galaxy has changed shape. The past once again is not confined. There is something quietly beautiful about this idea. Space is not a silent backdrop. it is a responsive medium. When something dramatic happens, when stars collapse, when massive objects collide, space-time itself trembles, and that trembling becomes part of the ongoing structure of the universe. Even more astonishing, physicists hope that one day we may detect gravitational waves from events even earlier in cosmic history, perhaps from the formation of the very first black holes, perhaps even from fractions of a second after the universe began expanding. If that happens, we would not simply be looking into the past with light, we would be listening to the oldest vibrations space has ever carried. Light shows us frozen images. Gravitational waves let us feel motion, and together they suggest something profound. The universe does not discard its history, it transmits it, not as a static record, not as a neatly filed archive, but as expanding patterns, waves moving outward, carrying the imprint of what once occurred. The splash is brief, the ripple endures, and somewhere even now space itself is still whispering about things that happened before there were oceans on Earth, before there were continents, before there was life to wonder about any of it. The past in its quiet way is still travelling. Light can echo, space can ripple, but there is one signal more ancient than any star we can see, more distant than any black hole merger we have yet detected. It does not come from a single dramatic event. It comes from the moment the universe first became transparent. To understand it, we have to imagine a time before there were stars at all. In its earliest phase, the universe was unimaginably hot and dense, not just warm, not just glowing, but so energetic that atoms could not exist in stable form. Electrons and protons moved freely in a kind of luminous fog. Photons, the particles of light, could not travel very far without colliding with these charged particles. They scattered constantly, bouncing in random directions. The universe was bright but opaque. It was like standing inside a thick, glowing mist. Light was everywhere, but it could not move freely across long distances. Every photon's journey was interrupted almost immediately. Then something subtle but profound happened. As the universe expanded, it cooled. Expansion is not simply motion outward into emptiness. It is space itself stretching. And when space stretches, the energy of light spreads out, becoming gentler. Over hundreds of thousands of years, the temperature dropped enough that electrons and protons could combine into neutral atoms. This event is often called recombination, though in truth it was the first combination of this kind. When atoms formed, the fog lifted. Suddenly, photons no longer scattered constantly. They were free to travel in straight lines. In that moment, about 380,000 years after the beginning of cosmic expansion, the universe released its first clear light. Those photons have been travelling ever since. We call this ancient glow the cosmic microwave background, often shortened to CMB. It is not visible to our eyes because over billions of years of expansion, its wavelength has stretched. What began as brilliant high-energy light has cooled and lengthened into microwave radiation, faint and uniform. Yet it still arrives. From every direction in the sky, this ancient light continues to wash over Earth. Specialized instruments can detect it as a subtle glow, almost perfectly even in all directions, with tiny variations in temperature. Those variations are incredibly small, differences of only a few millionths of a degree. But within those minute fluctuations lies the blueprint of everything that would come later. If you could see the cosmic microwave background with your eyes, the entire sky would shimmer faintly with the memory of a universe just beginning to take shape. It is sometimes described as the oldest photograph we will ever have, but that description is not entirely accurate. A photograph is static, fixed in time. The cosmic microwave background is still arriving. It is not a picture stored in an album. It is light that has been travelling for nearly 13.8 billion years and has only now reached our detectors. When you look up at the night sky, you are beneath this glow, even if you cannot see it. There is something deeply humbling about that thought. The Earth did not exist when this light began its journey. The Sun had not yet formed. The Milky Way galaxy was still assembling its spiral arms, and yet the photons released in that early clearing of cosmic fog have persisted across all of cosmic history. They have crossed expanding space. They have passed by forming galaxies and exploding stars. They have drifted through regions that would one day give rise to planets, oceans, and life. And now they arrive. The mathematics describing this process can be complex. Cosmologists often use equations relating the expansion of space to the cooling of radiation, connecting temperature and wavelength through proportional relationships. But you do not need the symbols to grasp the essence. As space stretches, light stretches with it. As light stretches, it cools. And because the universe has been expanding for billions of years, that ancient light has cooled into microwaves. The cosmic microwave background is not dramatic. It does not flare or pulse. It is steady, quiet, almost perfectly uniform. Yet it carries a message from a time when the universe was less than 1/1,000,000th of its current age. In those tiny temperature differences, slight warm and cool patches, lie the seeds of galaxies. Regions that were a little denser than average would, over billions of years, pull matter inward through gravity. Those regions became clusters of stars. Other regions remained emptier. The large-scale structure of the universe, the web of galaxies stretching across space, traces back to those almost imperceptible ripples. The past is not only preserved in light, it is written into the structure of everything around us. The cosmic microwave background is also remarkable because it is everywhere. Unlike light from a distant star which arrives from a specific direction, this ancient glow surrounds us completely. No matter where you point a detector, you will find it. It is as though the universe has wrapped itself in a faint, persistent memory. You're never outside it. And because this light has been travelling for nearly the entire history of the cosmos, it represents the deepest look back we can achieve with light alone. Beyond that time, the universe was opaque. There are ideas about detecting gravitational waves from even earlier moments, vibrations from fractions of a second after cosmic expansion began. But with light, this is the horizon, the first clear glow. Imagine standing in a vast dark hall just after the fog has cleared, seeing for the first time the outlines of a space that will one day become filled with stars and galaxies. That is what the cosmic microwave background represents, the moment visibility began. And that moment is still moving. Each second, new photons from that ancient epoch reach Earth. They are faint, but they are constant. They do not remember us. They do not change course. They simply arrive, completing journeys that began before there was a planet to receive them. The universe, in this way, does not discard its earliest chapters. It carries them forward. The oldest light is not a relic locked away. It is an ongoing arrival. And somewhere in that gentle, all-sky glow, the universe's first clear breath is still echoing. Not as a sound, not as a flash, but as a quiet background hum beneath everything we see. The ancient glow of the early universe surrounds us, arriving from every direction. It feels vast and impersonal, a memory from before there were stars like our sun, before there were planets or oceans or breath. But memory in motion is not only a cosmic phenomenon, it is happening much closer to home. Every second, Earth sends its own past outward. When sunlight reaches our planet, some of it is absorbed, warming oceans and land. Some of it is transformed by plants into chemical energy, and some of it reflects, It bounces off clouds, off mountain peaks, off deserts and forests and rooftops. That reflected light does not stop at the edge of the atmosphere. It continues outward into space. Each photon carries an imprint of what it touched. A photon that glances off the surface of the Pacific Ocean carries the shimmer of waves from that moment. A photon that reflects from a city at night carries the glow of electric lights arranged by human hands. A photon that leaves a forest canopy carries the pattern of leaves and branches that shaped its path. Most of these photons will travel forever without encountering anything significant. Space is vast, and the distances between stars are immense. But the key idea is simple. The image of Earth at this moment does not remain here. It expands outward in a growing sphere at the speed of light. Imagine an invisible shell expanding around our planet. At its surface is the boundary between what has already happened and what has not yet been reached by that information. The light leaving Earth tonight will form a spherical wave moving outward, 1 second per second in light years. 1 year from now, that shell will be 1 light year away. 4 years from now, it will brush past the nearest stars beyond our sun. Thousands of years from now, it will cross the broader structure of our galaxy. In principle, if there were an advanced civilization orbiting a distant star at just the right distance, and if they possessed instruments sensitive enough to capture faint reflected light from our planet, they might observe Earth as it was years ago, the Earth of ancient forests, the Earth of early civilizations, even the Earth of dinosaurs, its light still travelling outward, layer upon layer. The universe is not only an archive of distant galaxies, it is also an expanding record of our own world. There is something quietly beautiful about this idea. It suggests that moments are not confined to the place they occurred. They radiate outward. They become part of a larger pattern, and this is not unique to planets. Every object that reflects or emits light participates in this broadcast. The moon, glowing in reflected sunlight, sends its pale image outward. The rings of Saturn shimmer and transmit their patterns. Even your own face, lit by a lamp in a quiet room, is contributing photons to an ever-growing sphere of information. The mathematics behind this expansion is straightforward, even if we do not write it down. Light moves at a fixed speed. That speed links distance and time. 1 year of travel corresponds to 1 light year of distance. 1 minute corresponds to a certain number of kilometers crossed. The connection is direct and unwavering. Because of that steadiness, we can think of time not only as something flowing forward, but as something expanding outward. Each moment forms a spherical boundary in space. The Earth you knew 10 years ago, its seasons, its weather, its cities, exists not only in memory. Its light is currently about 10 light years away, passing by stars that were once only points of brightness in our sky. The Earth of 100 years ago is 100 light years away, its faint reflection drifting past clusters of stars that our ancestors could never have imagined visiting. Of course, this light becomes weaker with distance. It spreads out, thinning as it travels. Detecting it from far away would be extraordinarily difficult. But difficulty is not the same as impossibility. The information is there, diluted but not erased, and light is not the only thing we send outward. Radio waves, television signals, radar pulses, all of these are forms of electromagnetic radiation, like visible light but at different wavelengths. For about a century, humanity has been unintentionally broadcasting its technological presence into space. The earliest radio transmissions have now travelled roughly 100 light years in every direction, forming a faint, expanding bubble around our planet. Within that bubble are echoes of music, news, conversations, fragments of stories. They are incredibly faint by cosmic standards, but they exist. Earth, then, is not silent. It is luminous, not only in sunlight, but in the patterns of information it emits. This realization gently shifts the way we think about disappearance. When something happens here, a sunrise over a mountain range, a storm crossing the ocean, a quiet conversation in a kitchen, its light does not remain trapped. It joins the expanding shell. The present becomes past. The past becomes radiation. And that radiation becomes part of the universe's ongoing structure. There is a poetic symmetry here. We receive ancient light from galaxies billions of years old. We stand beneath the glow of the cosmic microwave background, still arriving from the dawn of time, and at the same time we contribute our own faint layer to the cosmic archive. We are observers, yes, but we are also participants. The Earth of this moment will not vanish when tomorrow comes. Its light will simply be farther away. And somewhere, in the vastness between stars, there are shells of Earth's past moving steadily outward, overlapping, expanding, never returning, but never truly disappearing either. The planet you stand on is not only turning beneath the sky, it is writing itself into space. The idea may feel abstract, but it is grounded in the simplest of principles. Light travels, and it does not turn back unless something bends it. Most of it simply continues, and so the past is not stored in a single place. It is dispersed, stretched into expanding spheres, growing larger every second. The Earth you know right now has already begun its journey into the wider universe, and in that sense, the past is not behind us. It is out there, travelling, patient, silent, and still on its way. Light carries images. Space carries ripples. Planets broadcast reflections of themselves into the dark. But there is a quieter archive, closer than the sky and older than any photograph of Earth. It is inside you. When you look at your hands in the soft light of a room, you see skin, lines, perhaps a faint scar or two. It feels personal, immediate, entirely yours, and yet the atoms that compose those hands are far older than your name. Hydrogen, the simplest element, was formed in the first few minutes after the universe began expanding. In those early moments, when the cosmos was still unimaginably hot and dense, simple nuclei formed, mostly hydrogen, some helium, and traces of lithium. That hydrogen has persisted ever since. It drifts through interstellar space, gathers into clouds, collapses into stars, combines into water, and circulates through living bodies. The hydrogen in the water you drank today may have existed for nearly 13.8 billion years. Heavier elements have a different story. Carbon, oxygen, nitrogen, calcium, iron, the elements that give structure to your bones and allow your blood to carry oxygen, were not created at the very beginning. They were forged inside stars. A star is not only a source of light, it is a furnace. In its core, under immense pressure and heat, hydrogen atoms fuse together, forming helium. Over time, as hydrogen becomes scarce, heavier fusion reactions occur. Helium can fuse into carbon. Carbon can contribute to the formation of oxygen. In the most massive stars, fusion proceeds through a chain of elements, building up to iron. The details of nuclear fusion are described by equations linking mass and energy, often summarized by the famous relationship that mass and energy are interchangeable, expressed in the compact form energy equals mass times the speed of light, squared. But we do not need to dwell in symbols to feel its meaning. When tiny amounts of mass are converted into energy in a star's core, that energy becomes the light and heat that radiate outward. Stars shine because matter transforms. When massive stars reach the end of their lives, they can explode as supernovae, scattering newly forged elements into space. Those elements become part of vast clouds of gas and dust. Over millions of years, gravity gathers those clouds into new stars and planets. Our Sun was born from such a cloud about 4.5 billion years ago. The Earth formed from the same swirling disk of material, and the atoms that would eventually become part of living organisms were already present in that mixture. When life emerged, it did not invent new matter, it rearranged what was already there. The carbon in your body was once inside a star that lived and died long before the Sun existed. The calcium in your teeth may have been part of a shell in an ancient ocean which itself was built from atoms formed in stellar cores. The iron in your blood, the element that allows hemoglobin to bind oxygen, was forged in the final violent moments of a massive star's collapse. You are not only observing the cosmos, you are made of it. And the story does not end with origin, it continues with exchange. The atoms in your body are not fixed in place for your entire lifetime. You inhale oxygen, you exhale carbon dioxide, you drink water, you eat food. Cells divide and die. Molecules are broken apart and rebuilt. Over the course of years, a significant portion of the atoms in your body are replaced. You're less like a statue carved from unchanging stone, and more like a river, a pattern that persists while the water flows through it. This continuity of pattern amid constant exchange is one of the quiet marvels of biology. The structure remains recognizable, the arrangement endures, but the individual atoms come and go, and when they leave, they do not vanish. Carbon atoms you exhale enter the atmosphere. Some may be absorbed by plants during photosynthesis. Those plants may be eaten by animals. The cycle continues. Water molecules evaporate, condense into clouds, fall as rain, seep into soil, and return to oceans. The boundary between you and the environment is porous. Matter circulates. There is comfort in this idea. It means that the past is not only recorded in distant starlight or in faint ripples of space-time. It is embodied in substance. The very material that composes you has travelled across cosmic history, passing through stars, through oceans, through countless living forms. The phrase stardust is sometimes used poetically, but it is also scientifically accurate. The heavier elements essential to life were created in stellar furnaces. Without those ancient stars, there would be no carbon chains, no complex chemistry, no living cells. When you take a slow breath, you are participating in a cycle, billions of years in the making, and one day the atoms that compose you will continue their journey. They will not retain your thoughts or memories, but they will persist. They will become part of soil, air, water, perhaps even new forms of life. The past, in this sense, is not a fading photograph. It is a continuous transformation. Matter does not forget its origin. It carries it forward in new arrangements. Light shows us where we have been. Gravitational waves let us feel ancient motion. The cosmic microwave background surrounds us with the glow of the early universe. And within your own body is another archive, not written in ink or stored in images, but structured in atoms that have endured across epochs. You're not separate from the universe's history. You're one of its current expressions. The ancient fire of stars has become bone and breath. The earliest hydrogen drifts through your cells. The past has not been discarded. It has been reassembled, and as you sit quietly, now you're not only looking back through time, you're carrying it. If you're made of ancient fire, then you're also made of movement. It is easy to imagine your body as something solid and stable, like a statue carved from stone. The outline appears consistent from day to day. Your reflection looks familiar. Your hands feel the same as they did yesterday. But beneath that appearance of steadiness, there is constant exchange. With each breath, you draw oxygen into your lungs. That oxygen diffuses into your bloodstream and binds to iron atoms inside hemoglobin molecules. Those molecules travel through arteries and capillaries, delivering oxygen to cells that use it to release energy from food. In that process, carbon atoms, which may once have been part of a leaf or drifted through the air centuries ago, are rearranged and eventually released back into the atmosphere as carbon dioxide. The air you exhale is not entirely new. It is part of a planetary cycle. Water moves through you in a similar way. The molecules that make up a glass of water may have once been inside a glacier, or inside a cloud, or inside another living organism. You drink them. They become part of your cells, your blood, your tissues. Later they leave, evaporating into the air or returning to the soil. The atoms that compose you are on loan. Biologists estimate that over the course of years, a large fraction of the atoms in your body are replaced. The exact percentages vary by tissue. Some cells, like those lining your gut, turn over rapidly. Others, like certain neurons in the brain, can persist for decades. But even in those longer-lived cells, molecules are continuously repaired and renewed. You're not a fixed collection of atoms, you're a pattern sustained by flow. This is a subtle but important shift in perspective. It means that identity does not reside in a particular set of particles. It resides in the organization, in the relationships between them, in the structure that endures even as components come and go. If you think of a river, you understand this intuitively. The river has a name. It has a recognizable shape. It winds through valleys and past cities. Yet the water in the river today is not the same water that was there last month. The pattern persists. The contents change. The past, then, is not only something carried in distant light or in the ancient origin of atoms, it is also embedded in cycles. Consider the carbon cycle. Carbon moves from the atmosphere into plants through photosynthesis. Plants are eaten by animals. Animals respire and return carbon to the air. Some carbon becomes buried in sediments, and over geological timescales transforms into fossil fuels. When those fuels are burned, the carbon re-enters the atmosphere. The same atoms can move through rock, air, water, leaf, muscle, and back again. In this circulation, the past is not erased, it is transformed. Even the cells in your body carry internal clocks. Rhythms that trace back to the rotation of the Earth. The circadian cycle, roughly 24 hours long, is a biological reflection of our planet's day-night rhythm. Deep inside your cells, networks of genes turn on and off in repeating patterns, synchronized to light and darkness. Your heartbeat follows electrical pulses generated by specialized cells in the heart. Your breathing follows neural rhythms in the brainstem. These are not mechanical repetitions imposed from outside. They are internal oscillations shaped by evolution across millions of years. Time is written into your physiology, and evolution itself is another archive. The DNA inside your cells carries sequences that have been refined and modified over vast stretches of time. Segments of genetic code trace back to ancient ancestors. Some genes are shared not only with other humans, but with plants, fungi, and bacteria. The molecular machinery that allows your cells to produce energy, for example, is deeply conserved, a testament to life's shared origins. In that sense, you carry a library inside every cell. The letters of DNA, often abbreviated as A, T, C, and G, represent different chemical bases arranged in sequences. Scientists use symbols to describe these sequences, but you do not need to picture the letters to understand the idea. Think of DNA as a long-coiled instruction set, copied and passed down through generations. It is a record of survival, adaptation, and change. Your existence is the latest line in a story that stretches back billions of years. This continuity does not mean that everything is preserved in pristine detail. Mutations occur, genes are lost or rearranged, environments shift. but the overall structure, the ability of life to replicate and adapt, persists. Atoms circulate, molecules exchange, patterns endure, and all of this happens within the larger framework of physics, where matter and energy are conserved. In simple terms, the total amount of energy and matter in a closed system remains constant, though it may change form. When wood burns, it does not vanish. It transforms into heat, light, gases, and ash. The arrangement changes. The components persist. This conservation is not absolute in every conceivable situation. Modern physics allows for subtle complexities, but as a guiding principle in everyday processes, it holds true. The universe rearranges more than it deletes. When you sit quietly, breathing in and out, you are participating in that rearrangement. Atoms enter and leave. Energy flows through metabolic pathways. Signals pulse through neurons. The pattern of you remains recognizable, even as the material composition shifts. There is something deeply reassuring in this fluid stability. It suggests that the past does not simply fall away behind us. It becomes part of ongoing cycles. The carbon in your body may once have been part of an ancient tree. The calcium in your bones may have passed through multiple organisms before reaching you. The hydrogen in your cells may predate the Earth itself. You're not isolated from time, you're threaded through it. And as you exchange atoms with the air, the water, the soil, you're quietly contributing to future arrangements. The matter that composes you will continue its journey long after your current pattern dissolves. The endless exchange is not a loss, it is continuity in motion. The past is not only out there in expanding shells of light, it is circulating here in breath and blood and soil. You're both archive and participant, a temporary shape in a much older flow. Light travels outward. Gravitational waves ripple across space. Atoms circulate through stars, oceans, and bodies. Matter is rearranged but not erased. And yet, in daily life, time feels like a one-way street. You remember yesterday. You do not remember tomorrow. A glass can fall and shatter on the floor, but the scattered shards do not leap back together into a perfect shape. A drop of cream swirls into coffee and disappears into a soft brown mixture. It does not spontaneously separate itself back into white and black. If the universe preserves so much of its past, why does it feel as though time only moves forward? The answer lies in a concept that sounds technical, but can be understood through simple images: entropy. Entropy is often described as a measure of disorder. That word can be misleading if taken too literally. It is not about messiness in a moral sense. It is about the number of ways something can be arranged. Imagine a neat stack of papers placed carefully on a desk. There are relatively few ways to arrange those pages in exactly that orderly stack. Now imagine scattering them across the room. There are far more possible ways for papers to lie randomly on the floor than there are ways for them to sit in a perfect stack. The scattered state corresponds to higher entropy because there are more possible configurations that look like scattered than configurations that look like perfectly ordered. This idea connects to the deeper laws of physics in a subtle way. On the microscopic level, at the scale of atoms and molecules, the fundamental equations describing motion are mostly symmetric in time. That means that if you record the motion of particles and play it backward, the equations still make sense. A collision between two particles obeys the same rules whether it unfolds forward or backward in time. There is no built-in arrow in those basic interactions. But when you have enormous numbers of particles, trillions upon trillions, statistical behavior dominates. While it is not impossible for scattered papers to jump back into a neat stack, it is unimaginably unlikely. The number of microscopic arrangements corresponding to disorder vastly exceeds those corresponding to order. Over time, Systems naturally evolve towards states that can be realized in more ways. This tendency is captured in what physicists call the second law of thermodynamics. In simple language, it says that in an isolated system, entropy tends to increase. The important word here is tends. It is not a rigid command imposed from outside. It is a statistical truth arising from probability. If you shuffle a deck of cards thoroughly, you're extremely unlikely to produce perfect order by chance. Not because it is forbidden, but because the number of disordered arrangements is vastly greater than the single ordered one. Entropy gives time its apparent direction. When a glass falls and shatters, the energy spreads out. The organized structure of the glass becomes a more dispersed arrangement of fragments. The total energy remains, but it is distributed differently. To reverse that process spontaneously would require an extraordinarily precise coordination of countless particles, something so improbable that, for all practical purposes, it never happens. The past feels fixed because lower entropy states are rare and fragile. Once the system has moved into a higher entropy configuration, returning to the exact earlier arrangement is statistically implausible. And yet, even here, nothing has been destroyed in a fundamental sense. When cream mixes into coffee, the molecules do not cease to exist. They simply spread out among the coffee molecules. In principle, if you had perfect knowledge of every position and velocity of every molecule, a level of detail far beyond any realistic measurement, you could, at least mathematically, calculate backward to the earlier state. In practice, that information becomes dispersed beyond retrieval. Entropy does not annihilate the past. It hides it in complexity. This distinction is gentle but profound. The arrow of time does not come from laws that erase history. It comes from laws that allow energy and matter to distribute themselves in ever more numerous configurations. The early universe, as far as we can tell, began in a state of extraordinary low entropy, highly ordered in a specific cosmological sense. That initial condition is one of the deepest mysteries in physics. Why was it so ordered? Why did it not begin already maximally disordered? Because it began that way, there has been room for entropy to increase ever since. Stars form, burn and fade, structures assemble and dissolve, heat flows from warmer regions to cooler ones, gradients smooth out. We experience this gradual levelling as the passage of time. Our own memories follow the same pattern. You remember the past because physical traces, neural connections, patterns of activity were formed in lower entropy states and then stabilized. You do not remember the future because it has not yet left such traces. Memory itself depends on asymmetry. And still, beneath this one-way flow, the deeper physical laws remain largely indifferent to direction. The equations describing gravitational attraction or electromagnetic interaction do not inherently prefer forward to backward. It is the overwhelming statistics of large systems that produce the arrow we feel. Time, then, is not a river with an absolute current imposed from outside. It is more like a slope created by probability. A slope that almost everything rolls down. When we say the past is gone, we're often responding to entropy. We see that broken glass does not reassemble. We see that aging does not reverse. We see that yesterday's exact arrangement of atoms will not spontaneously recreate itself, but at the microscopic level, the information about those arrangements has not been deleted. It has been diffused into vast numbers of particles and degrees of freedom. It has become part of the larger pattern. The past is not destroyed. It is dispersed. And that dispersion is what gives us the sense of forward motion. Entropy does not contradict the persistence of light, matter, or gravitational waves. It complements them. It explains why events radiate outward and why their detailed configurations become harder to reconstruct over time. The arrow of time is not a blade cutting the past away. It is a gradual spreading. The cream does not unmix, the glass does not unshatter, but the atoms involved continue their dance, carrying with them the imprint of what occurred, even if that imprint is now woven into an almost unimaginably complex tapestry. Time feels one way because probability leans that way, yet nothing truly vanishes. It only becomes more entangled with everything else. Imagine taking a book from a shelf, a real physical book filled with pages and ink, and placing it into a fire. The pages curl, the paper darkens, the words blacken and twist into smoke. Within minutes, the story seems gone. All that remains is ash drifting in the air and faint heat radiating outward. It feels like destruction. But from a deeper physical perspective, nothing has truly vanished. The paper has broken apart into gases and microscopic particles. The ink molecules have been rearranged. Heat energy has spread into the surrounding air. Photons of light have radiated outward, carrying tiny signatures of the process. If you could, in principle, track every particle and every photon involved, every fragment of ash, every molecule of carbon dioxide, every bit of energy released, you would find that the information about the book's original state is not erased. It is scrambled. The letters are no longer arranged on clean white pages. They are dispersed into smoke, heat, and motion. The story is no longer readable in the form you recognize, but the fundamental ingredients remain. They have simply taken on new configurations. This distinction between erased and scrambled lies at the heart of quantum physics. At the smallest scales, the laws that govern particles are described by equations that are, in a precise sense, reversible. If you know the complete state of a system, every amplitude, every phase, every quantum property, then, at least mathematically, you can evolve that state forward or backward in time. The formalism does not inherently delete information. In everyday language, this means that the universe keeps track. When two particles collide, their motion afterward encodes information about how they approached each other. When an atom absorbs light and later emits it, the outgoing photon carries a trace of that interaction. At the quantum level, processes unfold according to rules that preserve the total structure of information, even if that structure becomes unimaginably complex. Physicists sometimes describe this by saying that the evolution of a closed quantum system is unitary. But we do not need the word. We only need the idea. The rules do not allow information to simply drop out of existence. The smoke from the burned book contains the story, not as sentences you can read, but as patterns hidden within molecular positions and energies. If you could reverse every microscopic interaction, a feat so precise it borders on fantasy, you could, in principle, reconstruct the book. The practical impossibility of doing so does not imply fundamental loss. This is a subtle but powerful shift in thinking. It means that the disappearance we observe in daily life, the fading of heat, the mixing of cream into coffee, the crumbling of paper into ash, is not annihilation. It is diffusion. Entropy spreads information into degrees of freedom that are too numerous and too entangled for us to track. Quantum mechanics deepens this picture with another idea: entanglement. When two particles interact, their properties can become linked in such a way that describing one without the other becomes incomplete. Even if they later separate by vast distances, the quantum state describing them includes correlations between both. Information is not confined to one particle or one location. It is distributed across relationships. Think of entanglement as stitching. Two threads woven together cannot be described independently without losing something about the pattern. The pattern is in the connection. As systems interact, entanglement grows. Information spreads not by vanishing, but by becoming shared among more and more components. In a complex system, information becomes encoded in a web of correlations. This web can become so intricate that retrieving the original configuration is effectively impossible. Yet the underlying physical rules have not discarded anything. The universe, in this sense, refuses to crumple its pages. Even when stars explode, even when atoms decay, even when light redshift across billions of years of expansion, the transformations follow precise mathematical laws. Energy and momentum are conserved. Quantum states evolve continuously. There is no clause in the fundamental equations that says, at this moment, information shall cease to exist. Instead, information flows. It may become inaccessible to us. It may disperse into radiation travelling outward. It may become encoded in subtle quantum correlations beyond our current ability to measure. But it does not simply evaporate into nothingness. This perspective casts entropy in a new light. Earlier, we described entropy as a spreading, a movement towards states that can be realized in more ways. When a glass shatters, the details of its original structure become distributed among fragments, vibrations, and heat. If you do not track every microscopic variable, the information appears lost. But at the deepest level, it is embedded in the full configuration of the system. You can imagine the universe as an unimaginably vast ledger, recording interactions not in ink but in the evolving arrangement of fields and particles. Each event leaves a trace, though that trace may be diffused across distances and scales. This idea has remarkable implications. If information is never fundamentally destroyed, then the past cannot be erased in an absolute sense. It can become hidden, scrambled, diluted beyond recognition, but not eliminated from the fabric of reality. There is a quiet elegance in that. It suggests that the universe is not wasteful with its history. It does not tear pages out of its own book. It only rearranges the sentences into forms we may struggle to read. Of course, there is one place where this comforting principle seems to falter: black holes. These strange objects, formed when massive stars collapse under their own gravity, appear to swallow everything that crosses their boundary. Light cannot escape. Matter cannot escape. Information, it would seem, cannot escape. If something falls into a black hole, and the black hole eventually evaporates through a subtle quantum process known as Hawking radiation, does the information about what fell in disappear forever? If so, that would challenge the deep principle that quantum evolution preserves information. It is here, at the edge of darkness, that the universe presents one of its most delicate puzzles. But before we step into that shadowed territory, it is worth resting in what we've seen so far. Burn a book, and the story is scrambled, not erased. Mix cream into coffee, and the pattern dissolves into complexity, not nothingness. At the quantum level, interaction weave information into ever wider networks of correlation. The universe, it seems, is a relentless record keeper. Even when we cannot read the record, it remains written in the evolving state of everything that exists. And that makes the question of black holes all the more intriguing. If the universe never crumples its pages, what happens when an entire library falls beyond a horizon from which nothing returns? Black holes are often described as cosmic devourers. When a massive star exhausts its fuel, gravity can pull its core inward with such intensity that nothing can resist. Matter collapses, density rises, a boundary forms around the collapse region, a surface beyond which escape is no longer possible. This boundary is called the event horizon. Cross that horizon, and even light cannot return. At first glance, this seems like the ultimate eraser. If information about a book, a star, or a particle falls into a black hole and nothing escapes, then surely that information is gone. For decades, this question quietly unsettled physicists. In the 1970s, Stephen Hawking made a remarkable discovery. By combining ideas from quantum mechanics and general relativity, he showed that black holes are not entirely black. Because of subtle quantum effects near the event horizon, pairs of particles can briefly form from the vacuum. In rare cases, one particle falls into the black hole while the other escapes. To a distant observer, it appears as though the black hole is emitting radiation. This faint glow is now known as Hawking radiation. Over incredibly long timescales, this radiation would cause a black hole to lose mass and eventually evaporate. For a stellar mass black hole, this process would take far longer than the current age of the universe. But in principle, it happens. And here is where the puzzle sharpens. Hawking's original calculations suggested that the radiation emitted by a black hole is purely thermal. In simpler language, it looks like random heat. If that is true, then when the black hole fully evaporates, all that remains is featureless radiation, no trace of the detailed information about what fell inside. The book burned in the fire could, in principle, be reconstructed from its dispersed particles. But if a book were dropped into a black hole, and the black hole later evaporated into random radiation, it would seem that the information about the book has been permanently erased. That conclusion clashes with the principle we just explored, that quantum evolution does not destroy information. Thus emerged what became known as the black hole information paradox. It is not a dramatic contradiction exploding physics overnight. It is a quiet tension between two deeply trusted ideas. On one side stands general relativity, describing gravity and space-time with extraordinary accuracy. On the other side stands quantum mechanics, whose predictions have been confirmed in countless experiments. Each works beautifully in its domain. But when combined in extreme conditions, such as near a black hole's horizon, they appear to disagree. The image is almost poetic. Imagine a vast library. Books line its shelves, each one representing a detailed state of matter and energy. Now imagine that the shelves begin to collapse inward, falling behind a curtain from which no one can retrieve them. Later, the library itself fades into a fine mist of warm air. If that mist carries no imprint of the books it once held, then the stories are gone. But the universe, as we have seen, seems reluctant to erase its stories. Over the past few decades, many physicists have worked to resolve this paradox. While the full solution remains an area of active research, there is growing consensus around a reassuring idea. Information is not lost, even in black holes. One line of reasoning suggests that the information about what falls into a black hole is somehow encoded on the event horizon itself. Instead of being swallowed into an inaccessible interior, the information may be stored in subtle quantum correlations on the boundary. This perspective connects to the broader idea that the maximum amount of information that can fit within a region of space is proportional not to its volume, but to the area of its surface. This insight is sometimes described through what is called the holographic principle. The analogy is simple. A hologram is a two-dimensional surface that encodes a three-dimensional image. Similarly, the surface of a black hole may encode the information about everything within. If this is true, then the event horizon is not a destroyer, but a kind of membrane that preserves information in a highly compressed form. More recently, calculations involving the detailed pattern of Hawking radiation have suggested that, over time, subtle correlations in the emitted radiation may carry away the information that once fell inside. The radiation would not be perfectly random after all. It would contain faint, intricate structure, a scrambled but complete encoding of the black hole's history. The mathematics behind these results can be intricate, involving entropy curves and quantum entanglement across space-time. But at heart, the emerging picture is gentle. Even black holes may not violate the universe's habit of record-keeping. Information may be stretched, encoded, and dispersed in ways that defy ordinary intuition. But it is not simply deleted. There is something deeply reassuring in that possibility. The most extreme objects in the universe, regions where gravity bends space to its limits, do not appear to tear pages out of reality's book. Instead, they compress the pages, hide them in unfamiliar formats, and release them slowly over cosmic timescales. The paradox is not fully settled. Physicists continue to debate details. New ideas are proposed, calculations are refined, but the prevailing direction of thought leans toward preservation rather than erasure, and that aligns with everything we have seen so far. Light carries images across billions of years. Gravitational waves carry motion. Atoms circulate through stars and living bodies. Entropy disperses but does not annihilate. Quantum evolution preserves structure beneath complexity. Even at the edge of darkness, the universe seems unwilling to forget. If black holes do not truly erase information, then the principle holds even in the most extreme corners of reality. The past may be hidden. It may be scrambled into patterns so subtle that no civilization could reconstruct them. But it remains part of the unfolding whole. And if information is so persistent, then perhaps our understanding of time itself needs to shift. Perhaps time is not a simple container through which events pass and disappear. Perhaps it emerges from deeper patterns of connection. If that is so, then before and after may not be as fundamental as we imagine. Beyond the horizon of black holes lies not only darkness, but a question about the very nature of time, and that question will guide us into the next layer of our exploration. Up to this point, we have treated time as a kind of stage. Events happen, light travels, atoms rearrange, entropy increases, information spreads. Time feels like the backdrop against which all of this unfolds, steady, silent, unquestioned. But what if time is not the stage? What if it is something that arises from deeper relationships? In everyday life, time feels fundamental. Seconds tick on a clock. Days pass as the Earth rotates. Years accumulate as we circle the Sun. But those are physical processes. Rotations, orbits, oscillations of atoms. They are not time itself. They are changes we use to measure it. Modern physics has already blurred our intuitive sense of time. Relativity tells us that time does not flow identically for everyone. It stretches and compresses depending on motion and gravity. Quantum mechanics tells us that at the smallest scales, systems are described not by definite trajectories, but by probability amplitudes, patterns that evolve according to mathematical rules. Some physicists have taken a bold step further. They suggest that time may not be a fundamental ingredient of reality at all. Instead, time might emerge from entanglement. To understand this idea, imagine two particles created together in a single quantum process. Their properties are linked. Even if they later separate, the description of one is incomplete without the other. They are part of a shared state. Now imagine extending this principle not to two particles, but to vast collections of them, to entire systems. When subsystems become entangled with one another, correlations build up. Information becomes distributed across relationships. Some theoretical work suggests that if you look at a sufficiently large quantum system and divide it into parts, the correlations between those parts can give rise to something that behaves like time. In simplified terms, one part of the system can act as a clock for another. The sequence of changes we call before and after may arise from the way entanglement grows between subsystems. Rather than time existing independently and driving entanglement, entanglement itself might generate the structure we interpret as temporal flow. Think of a woven fabric. Each thread alone has direction and tension, but it is the crossing of threads, the pattern formed by their interconnection, that gives the fabric its structure. If you remove the stitching, the pattern dissolves into loose strands. Time, in this picture, is not a single thread running through the universe. It is the pattern created by countless connections. There are mathematical models in which the global state of a system does not explicitly include time as a variable. Instead, what we perceive as time emerges when one part of the system is compared to another. Change is defined relationally. You might picture two dancers moving together. If you observe only one dancer in isolation, their motion may seem ambiguous. But when you see both together, their coordinated steps define a rhythm. The rhythm is not an independent object. It arises from the relationship. Similarly, time could be a relational rhythm within the universe's quantum state. This idea does not mean that clocks are illusions or that time is imaginary. It suggests that what we call time may be a higher-level feature of deeper, timeless laws. The equations governing fundamental interactions often treat time as a parameter, a way of indexing change. But some attempts to unify quantum mechanics with gravity hint that, at the most basic level, the description of the universe might not include a flowing time variable in the usual sense. Instead, there may be a static structure, a vast configuration of fields and correlations, from which temporal experience emerges when viewed from within. If this sounds abstract, it is, but the emotional core is gentle. Earlier we asked whether the past truly disappears. We saw that light carries it forward, that gravitational waves ripple with it, that atoms embody it, that entropy disperses it but does not erase it, and that quantum laws preserve information even in extreme conditions. If time itself is emergent, then the distinction between past and present may not be as fundamental as we assume. What we experience as a sequence, one moment following another, could arise from the way our minds, embedded in a vast entangled network, trace patterns of correlation in such a picture. The universe is not a film strip unspooling frame by frame. It is more like a tapestry whose structure contains every thread at once. The sense of movement comes from how we trace lines through that tapestry. This does not deny change, it reframes it. From inside the system, change feels real. Memories form, expectations build, entropy increases. But from a deeper vantage point, all states may coexist in a structured whole, linked by relations rather than ordered by an external clock. Some approaches to quantum gravity explore precisely this possibility. They attempt to describe space-time, the combined fabric of space and time, as something that arises from entanglement patterns. In these models, geometry itself may be a manifestation of quantum correlations. Space emerges from connection. Time emerges from relation. If that is true, then the past is not a place that has slipped away. It is a region of the tapestry connected to the present by intricate threads. We experience it as behind us because of how entropy and memory function within our local subsystem. But at the deepest level, reality may not distinguish so sharply between was and is. It is important not to overstate this. These ideas remain areas of active research. Physicists debate the details. The mathematics is complex and still evolving. There is no final consensus. Yet the direction of inquiry is striking. The universe may not be fundamentally built from a ticking clock. It may be built from relationships, and if time crystallizes out of entanglement, then the arrow we feel is part of a larger pattern, not an absolute boundary. In that light, asking where the past goes becomes less about disappearance and more about perspective. If time is woven from connection, then every moment is part of a greater whole, not isolated, not discarded, but integrated. The flow we feel may be the way our local patch of the tapestry experiences its own unfolding, and beyond that, unfolding, the structure itself endures. If time may emerge from deeper relationships, then the idea of a single, universal now becomes even more delicate. In everyday life, it feels obvious that there is one present moment shared by everyone. Right now, as you listen, it seems natural to imagine that somewhere across the world, other people are experiencing this same instant. Different locations, different circumstances, but the same now. Relativity gently unsettles that intuition. At the beginning of the 20th century, Albert Einstein proposed that the speed of light is the same for all observers, no matter how they are moving. This simple statement has profound consequences. If light travels at a constant speed, about 300,000 kilometers per second, then measurements of time and space must adjust to preserve that constancy. The result is something called relativity of simultaneity. Imagine two lightning bolts striking the front and back of a long train at the same time, as judged by someone standing on a platform beside the tracks. Light from both strikes travels toward the observer at equal distances and reaches them simultaneously. To the observer on the platform, the strikes were simultaneous. Now imagine someone sitting in the middle of that moving train. As the train travels forward, the person inside is moving toward the light from the front strike and away from the light from the rear strike. Because light speed is constant, the observer on the train will receive the light from the front strike before the light from the rear strike. To them, the front strike happened first. Two observers, one event, different judgments about simultaneity. Neither is wrong. This is not an illusion or a trick of perception. It is a fundamental feature of how space-time is structured. When observers move relative to one another, their slices of now tilt differently through space-time. The idea can feel abstract, but its effects are measurable and real. Global Positioning System satellites, which allow your phone to determine its location, rely on extremely precise clocks. These satellites orbit Earth at high speeds and at higher altitudes, where gravity is slightly weaker. According to relativity, both motion and gravity affect the rate at which time passes. The satellite clocks tick at slightly different rates compared to clocks on Earth's surface. The differences are tiny, measured in microseconds, millionths of a second. But if engineers did not account for them, the positioning system would accumulate errors of several kilometers each day. Relativity is not philosophical speculation. It is built into the devices we use. What this means, gently but unmistakably, is that there is no universal cosmic bell ringing to mark a single shared present. Each observer carries their own now, defined by their state of motion and gravitational environment. You might picture each person surrounded by a softly glowing bubble representing their present moment. These bubbles overlap and intersect, but they're not identical. What counts as happening now for one observer may already be slightly in the past or slightly in the future for another, depending on their relative motion. This does not disrupt daily life because the differences are usually minuscule at ordinary speeds. When you walk across a room, the time dilation is far too small to notice, but the principle remains. The universe does not privilege one global present. In physics, space-time can be represented as a four-dimensional structure with 3 dimensions of space and one of time woven together. Events are points in this structure. Observers trace paths, called world lines, through it. What each observer considers now corresponds to a particular slice through space-time, a slice that depends on their motion. If you rotate that slice by changing speed, the set of events considered simultaneous changes. This perspective challenges the intuitive sense that the present is a thin, universal layer separating past from future. Instead, reality resembles a vast landscape. Different observers carve different cross-sections through it. This does not mean that anything goes, or that causality breaks down. Light cones, the regions defined by the speed of light, ensure that causes precede effects in consistent ways. If one event can influence another, they lie within each other's light cones. That structure preserves the order of cause and effect across observers. But outside those causal boundaries, the ordering of distant events can differ. If two galaxies are so far apart that no signal travelling at light speed could pass between them within a given time, then different observers may disagree about which galaxy's event occurred first, and there is no absolute fact of the matter beyond those observer-dependent descriptions. The absence of a universal now does not erase the past, it reframes it. Earlier we saw that light carries ancient images, that gravitational waves transmit ancient motion, that atoms embody ancient processes, and that entropy disperses but does not destroy. Now we see that even the slicing of time into past, present and future depends on perspective. This perspective dependence aligns naturally with the idea that time might emerge from relationships. If there is no absolute global clock, then the flow of time may be deeply tied to the structure of interactions and measurements within each local frame. The present becomes less like a razor edge dividing existence and more like a local horizon, shaped by motion, gravity and connection. And that invites a deeper question. If there is no single cosmic now, then how should we picture the whole timeline? Does the past still exist in some sense? Is the future already laid out? Or is only the present real? Different philosophical models attempt to answer those questions in different ways. But before we step into those possibilities, it is worth pausing with this realization. The universe does not synchronize itself to a universal drumbeat. There is no master clock at the center of reality. Instead, each observer carries their own rhythm, their own slice of the tapestry, their own gently glowing present, overlapping with others, intersecting through light cones but never identical. And within that shifting structure, the past remains embedded in signals, matter and correlations. The absence of a single cosmic now does not make time less real, it makes it richer. If there is no single cosmic now, then the structure of time may be different from how we instinctively picture it. Philosophers and physicists have proposed several ways to imagine the overall shape of time. None of them are proven in the way a laboratory experiment is proven. They are interpretive frameworks, ways of understanding what our best physical theories might imply about the nature of reality. Three of these pictures are especially well known. The first is sometimes called eternalism, or more poetically, the block universe. In this view, the universe is like a vast four-dimensional sculpture. All events, past, present, and future, exist within this structure. Just as a marble statue contains every contour at once, the block universe contains every moment at once. The past doesn't vanish. The future is not yet to be created. Instead, every event occupies its place in the space-time structure. From this perspective, the flow of time is not something happening to the universe. It is something experienced by observers moving along their world lines through the block. Imagine a completed novel. All chapters exist simultaneously in the book. The beginning, the middle, and the end are all there on the pages. But as a reader, you experience the story sequentially, turning pages one at a time. The unfolding is in your experience, not in the physical existence of the chapters. In the block universe picture, reality is the complete novel. Your consciousness is the reader. This view fits naturally with relativity. Since there is no universal present slicing across the cosmos, it becomes tempting to think of space-time as a whole, a single, structured entity containing all events. The second picture is presentism. In this view, only the present is real. The past existed but no longer does. The future does not yet exist. Reality is like a candle flame. Only the tiny region at the tip is real, flickering into existence moment by moment. Presentism aligns with our everyday intuition. We remember the past, we anticipate the future, but only now feels solid and tangible. When we say something no longer exists, we are often expressing this presentist instinct. However, presentism faces challenges when combined with relativity. If there is no universal present, then which now is the real one? Different observers disagree about which distant events are simultaneous. If only the present exists, whose present defines reality? This tension does not make presentism impossible, but it complicates it. The third picture lies somewhere in between. It is often called the growing block universe. In this model, the past and the present are real, but the future is not yet. Reality is like a wall being painted. The painted portion, the accumulated past, remains fixed. The unpainted portion, the future, does not yet exist. The boundary between painted and unpainted represents the present, constantly advancing. In this view, the past does not disappear. It remains part of reality's structure. But the future is open. This model captures a common intuition that what has happened is fixed and real, while what has not yet happened remains uncertain. Each of these pictures attempts to make sense of the same underlying physics. The block universe emphasizes the geometric structure of space-time revealed by relativity. The growing block preserves a sense of objective passage while granting reality to the past. Presentism keeps reality tightly anchored to the immediate moment. None of these models require equations to appreciate. They are conceptual lenses. What matters for our exploration is how each treats the past. In the block universe, the past is not gone. It is simply located at different coordinates within space-time. The dinosaurs are not erased. Their events occupy earlier regions of the block. In the growing block, the past remains part of the existing structure. In presentism, the past is not currently real, but its traces persist in memory and physical records. Notice something gentle here. Even in the strictest presentist picture, the past leaves traces. Fossils remain embedded in rock. Light from distant galaxies carries ancient images. Neural patterns in your brain encode memory. Entropy preserves the direction of change. Information is not fundamentally destroyed. The debate is not about whether the past has influence. It is about whether it continues to exist as part of reality structure. The block universe can feel unsettling at first. If the future already exists in the block, does that mean it is fixed? Does it undermine freedom or uncertainty? These are deep philosophical questions, and different thinkers answer them in different ways. Some argue that even in a block universe, the experience of choice remains meaningful because the structure includes the entire web of decisions and consequences. Others prefer models in which the future remains open. For our purposes, it is enough to notice that physics itself does not clearly mandate one interpretation over the others. The mathematical structure of relativity is compatible with the block view. Quantum mechanics introduces elements of indeterminacy. The exact relationship between these features remains an area of ongoing exploration. What remains consistent across interpretations is this: the past is not easily dismissed. Whether it exists as a region of space-time, as a growing portion of reality, or as a set of physical traces embedded in the present, it is woven into the structure of what is. The idea that time might be a completed sculpture, a growing wall, or a flickering flame offers different emotional textures. The sculpture suggests permanence and wholeness. The growing wall suggests continuity and accumulation. The flame suggests immediacy and renewal. Perhaps none of them is entirely complete. Perhaps reality includes elements of each perspective. What is certain is that the simplistic idea of time as a river washing events into oblivion no longer fits comfortably with modern physics. Light continues to travel, gravitational waves continue to ripple, atoms continue to circulate, information continues to persist in intricate forms. Relativity dissolves the notion of a universal now. Entanglement hints at deeper relational structures. Against this backdrop, the past feels less like a discarded shadow and more like a layer within a larger pattern. Whether that pattern is a block, a wall, or a flame, it is not empty behind us. And as we return from these broader philosophical vistas, there is one more layer to examine: the texture of the present itself. If the present is not a sharp boundary, but a region shaped by light delays, entropy, memory, and perspective, then perhaps it is softer than we think. Perhaps the present is not a knife edge separating past and future. Perhaps it is a blur. If the universe may be a block, a growing wall, or a flickering flame, then what exactly is this thing we call now? It feels sharp. When you pause and notice your breathing, there seems to be a precise moment in which the air enters your lungs. When you hear a sound, it seems to occur at a definite instant. When you look at a clock, the second hand appears to mark a specific point in time. But this sharpness may be more impression than reality. Earlier we saw that light takes time to travel. The sunlight warming your face left the sun about 8 minutes ago. The starlight reaching your eyes tonight may have begun its journey years, centuries, or millions of years ago. Even the face in your mirror is a tiny fraction of a second in the past. What we call the present is already layered with delay. Your brain itself introduces further softness. Neural signals travel at finite speeds, far slower than light. When photons strike your retina, they trigger chemical reactions that generate electrical impulses. Those impulses travel along neurons, pass through synapses, and are integrated across different regions of the brain. The experience you call seeing is constructed over tens to hundreds of milliseconds. In that time, the world continues to change, yet your perception feels continuous and unified. This suggests that the present is not an infinitesimally thin slice. It is more like a short window, a span within which sensory information is gathered and woven into a coherent experience. Psychologists sometimes refer to this as the specious present, the brief duration over which the mind integrates incoming signals into a single felt moment. It is not an official boundary in physics, but a feature of consciousness. The present, then, may be less like a razor edge and more like a soft blur. Within that blur are traces of the immediate past, light that has just arrived, sounds that have just reached your ears, neural patterns shaped by recent events. There are also anticipations, predictions your brain makes about what is about to happen next. The brain is constantly forecasting, using past experience to generate expectations about the near future. Perception is partly memory and partly prediction. This layering means that what you experience as now already contains echoes and projections. Add relativity to this picture, and the blur becomes even more textured. Because there is no universal present, the slice of space-time that defines your now is tied to your motion and gravitational context. Your present is local, shaped by your path through space-time. Add entropy, and you find that the present also carries a symmetry. Physical processes leave records, footprints in sand, fossils in rock, patterns in neurons. These records point toward what we call the past. There are no equivalent records of the future, because entropy has not yet had the chance to increase in that direction. The present is therefore not neutral territory. It is a region dense with traces of what has already unfolded. Imagine standing on a shoreline where waves overlap. Behind you, older waves have washed up and left damp patterns in the sand. Before you, new waves are forming, rising from deeper water. Around your feet, several waves intersect, some arriving, some receding. The exact boundary between past wave and future wave is not sharply defined. There is only motion and overlap. The present resembles that shoreline. Light from distant stars intersects with neural processing delays. Gravitational ripples pass through space. Atoms circulate through your body. Entropy spreads energy and information into wider configurations. Quantum correlations weave subtle connections beneath the surface. Within this complexity, your awareness traces a path. That path gives the impression of flow. We often imagine time as a river carrying us forward, but perhaps it is closer to a field in which patterns shift and overlap, and consciousness is the tracing of a particular line through that field. The blur of the present also explains why memory feels directional. You have access to records, neural and physical, of prior states. Those records shape your expectations and decisions. You do not have records of future states, because they have not yet left traces within your local subsystem. Entropy ensures that records accumulate in one direction. But beneath that asymmetry, the deeper physical laws remain largely reversible. The quantum evolution of a closed system does not inherently distinguish past from future. It is the growth of correlations and the spreading of energy that create the arrow we feel. In this layered present, past and future are not symmetric in experience, but they are connected in structure. The photons arriving now from distant galaxies are ancient. The atoms in your cells carry histories older than Earth. The gravitational waves passing through you may have begun their journey before life existed on this planet. All of these intersect within your local now. Your present is a meeting point. It is where ancient light arrives, where ancient matter circulates, where entropy continues its spreading, where entanglement patterns unfold. Seen this way, the present is not an isolated dot between two voids. It is a dense region of overlap, a convergence of trajectories. This perspective softens the question, where does time go? Time does not rush off into emptiness. It does not carry events into a separate container labelled past. Instead, events leave traces, in radiation, in matter, in correlation, that continue to influence the structure of reality. The present is not the edge of a cliff from which moments fall into oblivion. It is a region where multiple layers of the universe intersect, and within that intersection, you sit quietly, breathing, aware. The blur of now contains more than it seems. It contains arriving light from billions of years ago. It contains the recycled atoms of ancient stars. It contains neural echoes of yesterday and subtle predictions of tomorrow. It contains the arrow of entropy and the deep reversibility of quantum law. The present is not thin. It is thick with history, and if it is thick with history, then perhaps the past is not behind us at all. Perhaps it is woven through us. Time equals 2 seconds. We have wandered through light and gravity, through atoms and entropy, through philosophy and perception, and now the question returns in a quieter form. If the present is thick with history, if information is not easily erased, if light and waves and matter continue their journeys, then where does the past go? Perhaps the simplest answer is this: it does not go anywhere. It moves outward. Every event radiates consequences. When a star explodes, light spreads in all directions at a steady pace, about 300,000 kilometers each second. That light crosses galaxies and drifts through expanding space. Billions of years later, it may brush against a detector on Earth. The explosion itself is long over, but its signal is still in motion. When two black holes merge, space-time ripples. Those ripples continue outward, growing in radius, thinning in intensity but not vanishing. Long after the black holes have settled into silence, the wavefront still expands. When a leaf falls from a tree, photons scatter from its surface. Some are absorbed by the ground, others continue upward into the sky, joining the expanding shell of reflected sunlight leaving Earth. Each second, a new spherical layer forms around our planet, marking the boundary of that moment's light. The past does not sit behind us like a pile of discarded photographs. It spreads into space. Picture a series of translucent spheres, each one slightly larger than the last, centered on Earth. The smallest sphere contains the light emitted just a fraction of a second ago. The next contains light from 1 second earlier. Beyond that lies light from a minute ago, an hour ago, a year ago. Farther still are shells corresponding to ancient history. The light of cities now gone, of forests long vanished, of oceans shaped by climates that no longer exist. Those spheres continue expanding, merging with other expanding spheres from stars and galaxies. The universe is filled with such wavefronts, and light is only one layer. Gravitational waves also form expanding shells. When space-time trembles from a distant collision, that tremor spreads outward, intersecting with other ripples from other events. The cosmos becomes a superposition of waves, each carrying a fragment of history. Matter adds another dimension. The atoms forged in stars are not static relics. They circulate through planetary systems, through atmospheres and oceans, through living organisms. When you exhale, carbon atoms that once participated in ancient photosynthesis enter the air. When you inhale, you draw in atoms that may have drifted through countless other forms before reaching you. The past is not only out there in expanding radiation, it is here, circulating. Entropy ensures that configurations change, structures dissolve into more numerous arrangements, but that spreading does not annihilate the ingredients, it redistributes them. Information too persists in subtle ways. Quantum correlations encode traces of interaction. Even when details become inaccessible to practical measurement, they remain embedded in the evolving state of the universe. There is no cosmic incinerator where moments are burned into nothing. Instead, there is transformation. The language we use in daily life can be misleading. We say the past is gone, as if it were placed in a container and sealed away. But physics suggests something gentler and stranger. The past is diffused into space and matter. If you could travel outward at the speed of light, which nothing with mass can do but imagine it for a moment, you would ride the boundary between what has already happened and what has not yet been reached by its signals. You would trace the surface of those expanding spheres. Behind you would be regions of space that have received the news of an event. Ahead of you would be regions still unaware. Time, in this picture, resembles an ever-growing web of causal influence. Events propagate outward at finite speeds. Light defines the ultimate limit. Nothing can carry information faster than light in vacuum. That limit shapes light cones, the regions of space-time that can influence one another. Within those cones, causes lead to effects. Outside them, no influence has yet travelled. The past is therefore not a place behind us in space. It is a region within our light cone, the set of events that have already sent signals to us. The future is the region to which we can send signals. Between these regions lies the present, a moving boundary defined by the speed of light and the structure of space-time. When you raise your hand, photons reflect off your skin and begin their journey outward. That gesture becomes part of the expanding archive. It may never be detected by anyone beyond Earth. It may disperse into darkness. But it is not erased. The universe is constantly accumulating layers of influence. This does not mean that everything is accessible or meaningful forever. Over immense timescales, cosmic expansion will stretch wavelengths. Light will redshift, becoming longer and cooler. galaxies will drift beyond one another's observable horizons. Some signals will never reach certain regions. But the limitation of access is not the same as deletion. An unread letter still exists. The past is therefore not something that disappears into a void. It becomes part of a widening pattern, one that includes radiation, matter, correlations, and geometry, and you are part of that pattern. Your thoughts arise from neural processes shaped by evolutionary history. Your body is composed of atoms forged in ancient stars. Your presence alters electromagnetic fields and gravitational fields in subtle ways. You emit heat, light, and radio signals. You breathe in atoms and release others. You're both receiver and transmitter. The past is not static behind you. It is dynamic around you. It arrives as starlight. It moves outward as reflected photons. It circulates through breath and blood. It ripples in space-time. And in this sense, time does not carry moments away. Moments expand into the universe. The image is not one of loss, but of spreading. Each event becomes part of an ever-growing tapestry, woven from waves and particles and fields. The past is still travelling, and as it travels, it remains part of the same unfolding whole that you inhabit right now. If the past is still travelling, then so are you. It is easy to imagine yourself as stationary, sitting in a room, perhaps lying in bed, listening quietly. The walls feel still, the floor feels solid, the air feels calm. But at this very moment, you're moving through space at extraordinary speeds. The Earth rotates beneath you at roughly 1,000 miles per hour at the equator. At the same time, our planet orbits the Sun at about 67,000 miles per hour. The Sun itself orbits the centre of the Milky Way galaxy at nearly 500,000 miles per hour. And our galaxy moves through the larger cosmic web at speeds that stretch even further beyond everyday intuition. You're not standing still in the universe. You're travelling through an expanding archive. As you move, you intersect with layers of ancient light. Photons from distant stars pass through your eyes. Gravitational ripples from ancient mergers wash invisibly through your body. The cosmic microwave background, the afterglow of the early universe, passes through you every second, faint but constant. You're not separate from these signals. You are immersed in them. At the same time, you're contributing to the archive. Your body radiates heat as infrared light. That light travels outward at the same steady cosmic speed as starlight. It joins the expanding spheres of radiation leaving Earth. Your movements alter electromagnetic fields in subtle ways. Your voice sends pressure waves through air, which eventually convert into tiny molecular motions and heat. Even your thoughts, though not broadcast directly into space, arise from physical processes. Neurons exchanging electrical signals, ions crossing membranes, chemical gradients shifting in microscopic compartments. These processes are part of the same physical tapestry as stars and galaxies. You're not a spectator floating outside the system. You're a temporary arrangement of ancient matter, embedded in ongoing exchanges of energy and information. There is something deeply grounding in that realization. The atoms in your body have travelled for billions of years to reach this configuration. They will continue travelling after this configuration changes. The patterns of your neural activity are shaped by experiences, memories, and inherited genetic instructions that trace back through evolutionary history. You carry history not as a metaphor but as substance. When you speak to someone, your words alter their neural patterns, their responses alter yours. Information spreads not only through photons and waves in space, but through relationships between people. A conversation leaves traces in memory, which influence future decisions, which ripple outward through networks of interaction. In that sense, your actions are like gravitational waves in social space. They may begin locally, a kind gesture, a thoughtful sentence, a shared silence, but their influence can propagate far beyond the original moment. The universe's archive is not only physical, it is relational. Earlier we imagined expanding shells of light moving outward from Earth. Now imagine a different kind of sphere, one composed of consequences. Every action generates effects that spread through communities, ecosystems, and cultures. Some fade quickly, others persist for generations. You're both shaped by prior waves and generating new ones. The idea that time is a moving archive becomes personal here. You're not merely carried along by time as if it were a current sweeping you forward. You are part of the pattern that defines the current. The Earth spins, the galaxy turns, light travels, entropy spreads, information entangles, and within that grand motion, you breathe. It can be comforting to think that nothing truly vanishes, that the past is woven into matter and radiation, but it can also feel abstract. Bringing the perspective inward makes it tangible. When you look at the night sky, the photons entering your eyes are completing journeys that began long before you were born. At the same time, photons leaving your skin are beginning journeys that will continue long after this moment. You are a crossing point. Past signals arrive, future signals depart. Your body is not a barrier between past and future. It is a bridge. This does not mean that your individual experiences are etched permanently into the cosmos in a readable way. The information about your exact neural state at this moment will disperse into degrees of freedom too complex to reconstruct. But the physical processes that underlie it are part of the ongoing evolution of the universe. Nothing occurs in isolation. Even on the smallest scales, quantum interactions weave connections. Entanglement links systems, entropy spreads correlations, space-time curves around mass and energy. Light cones define the boundaries of influence. Within this intricate structure, you are a node composed of ancient atoms, animated by chemical reactions powered by sunlight, carrying a brain capable of reflecting on its own place in the cosmos. That capacity to pause and wonder is itself a product of billions of years of prior processes. It is the latest expression of a long chain of cause and effect. You're not at the end of that chain, you're in the middle of it. The archive is still expanding. New layers of light and influence are forming with each second. The present blur continues to accumulate traces that will shape what follows. When you take your next breath, oxygen molecules forged in ancient stars will bind briefly to iron atoms in your blood. Energy stored in chemical bonds, energy originally captured from sunlight, will sustain the neural activity that allows you to listen. You are, in the most literal sense, a traveller through a moving archive, and the archive travels with you. We began with a simple, unsettling question. Does the past disappear? At first glance it seems to. Moments slip away. Childhood becomes memory. Conversations fade into silence. Years pass, and we feel them receding behind us like a shoreline growing distant. But as we have moved gently through the layers of physics and philosophy, a different image has emerged. Light does not vanish, it travels. Gravitational ripples do not collapse into nothing, they expand. Atoms are not destroyed, they rearrange. Information is not casually erased, it is woven into wider patterns. Entropy does not incinerate the past, it disperses it into complexity. Relativity does not grant us a single universal present. It invites us to see time as structured and relational, and even the bold suggestion that time itself may emerge from entanglement hints that what we call past and future are not isolated compartments, but aspects of a deeper whole. Against this backdrop, time begins to feel less like a predator and more like a companion. We often speak of losing time or running out of time. The language carries urgency, sometimes anxiety. It suggests that time is something external, pressing against us, carrying away what we cherish. But the physical picture we have explored tells a quieter story. Time is not a force sweeping moments into oblivion. It is the structure within which transformation unfolds. When a star exhausts its fuel and collapses, it does not cease to matter. Its elements seed new systems. When light leaves a distant galaxy, it continues its journey across billions of years. When your body exchanges atoms with the air, those atoms continue their paths. Nothing stands outside this flow. You are not standing against time, you are moving with it. The fear that the past is erased often arises from our limited perspective. We cannot reconstruct every detail of yesterday. We cannot reverse entropy. We cannot retrieve photons that have long since passed beyond our reach. But limited access is not the same as annihilation. An unread book on a distant shelf still exists. A star beyond our observable horizon still burns, even if its light will never reach us. The past, as physics reveals, is not deleted from reality's ledger. It is integrated into its ongoing evolution. There is a profound calm in that realization. The night sky above you is filled with ancient arrivals. Some of the light entering your eyes tonight began traveling before human civilization existed. The cosmic microwave background, the faint afterglow of the early universe, continues to pass through you quietly. Gravitational waves from distant collisions ripple through space-time, unnoticed but persistent. You are surrounded by history, and you are contributing to it. The warmth radiating from your body travels outward. The air you exhale carries atoms into new cycles. The conversations you have shape neural patterns in others. Even the simple act of listening alters the configuration of your brain, leaving subtle traces that will influence what you think and feel tomorrow. Time is not stripping you of meaning. It is embedding you within a larger story. Perhaps the most comforting image is this: the universe is not forgetting. It is unfolding. Each moment becomes part of a growing pattern, not discarded, not burned into nothing, but transformed and carried forward in radiation, matter, and relation. Even when stars fade and galaxies drift apart, the laws governing transformation remain. Energy continues to shift forms. Information remains encoded in correlations. The tapestry evolves. From this vantage point, the question, where does time go, softens. Time does not go anywhere. It is the name we give to the unfolding of structure. It is the rhythm of change within a cosmos that preserves its own history in waves and atoms and connections. And if that is so, then your presence right now is not a fleeting spark swallowed by darkness. It is a node in an expanding network. You're a temporary configuration of ancient matter, animated by energy captured from sunlight, capable of reflection and awareness. That awareness allows you to contemplate the very fabric that gives rise to you. There is something beautifully recursive in that. The universe, through you, is reflecting on its own persistence. As the earth turns beneath you, as stars continue to burn and fade, as light travels across distances too vast to imagine, you remain part of the same continuum. Time is not rushing past you. It is moving with you. And when this particular configuration of atoms and thoughts eventually changes, as all configurations do, the matter will continue, the energy will continue, the web of influence will continue. Nothing will be erased. It will be transformed. So as you rest now, perhaps let go of the idea that the past is lost. It is in the light above you. It is in the atoms within you. It is in the patterns of your memory and the rhythms of your breath. The stars are still speaking. The earth is still turning. The universe is still expanding, carrying with it every layer of its unfolding story, and you are not outside that story. You're within it. Sleep peacefully, wherever and whenever you may be. Time is not an enemy chasing you forward. It is the gentle unfolding of a cosmos that never truly forgets.